We're going to jump into another chapter, which is about root locus technique. 여러분, so what is root and what is locus? What is root and what is locus? root는 근, 그지? 근데 우리가 제어 시스템에서의 근 뭘까? 폴이겠지, 폴. What about locus? locus는 궤적이지, 궤적. It's a trace. Okay? So, we're going to draw some graph in this chapter. Okay? Alright. So, well, here we have a closed loop system. And let's say this is my G, this is my H. Okay? And this was the midterm exam problem number 1. The open loop transfer function. What is it? KGH. This is the open loop transfer function. And closed loop transfer function is this. Right? So, for this, I'd like to ask you, what is the 0 and 4 for the open loop transfer function? The zeros for this is this, 4s for this is that. Right? This is the open loop 0 and open loop 4, right? What about this? So how can we find out this is the closed loop transfer function, right? So how can we find the closed loop 4 and the closed loop 0? How can we find? To find the pole for this closed loop system, we need to solve this characteristic equation. This must be 0, and we need to find out the root of this characteristic equation. 이거의 근을 찾아야 되잖아, 그지? So, which one is easy to find the poles? Open loop or closed loop? Open loop. By simply looking at, we know where the poles are. 보기만 해도 폴이 어디인지 알지? 그지? But for the closed loop system, 뭐 이렇게 좋냐? 뭐 이렇게 좋아? 누구야? 여자친구야? 나도 좀 같이 보자. 자, closed loop system에는 폴을 찾기가 좀 어렵지. It's a little difficult to find out closed loop pole. And even more, where is it? Gain K. It can be changed, right? So I can set K as 1, 10, 20, 100, 1000, whatever. It could be 0, it could be infinite, it could be 100, it could be anything, right? So depending on the value of K, the closed loop pole will be different. K 값에 따라 폴 당연히 바뀌겠지. So, as a control engineer, 만약에 if I might set K as 1, then we may be able to calculate the poles, right? So for that case, let's say since this is the third order system, there would be 3 poles, right? And let's say that in that case, 3 poles were here, let's say. But if I change gain K2, it could be here, 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 right? It could be anywhere. So I want to find out if I increase my gain K from 0, 여러분, I can increase my gain K from 0 to infinite, right? And what I want to know is, if I increase my gain K, increase, then how this pole will move. 그 관심 있잖아? I'm very interested in how these poles will be moving into, depending on how I can change the gain K. Because change of the location of the poles will make a different dynamic response. 폴의 위치가 다르면 다이내믹 리스폰스가 바뀌겠잖아. So, again, let me summarize in Korean. K 값을 바꾸면 클로즈 룹의 폴의 위치가 바뀔 거 아니야. 그럼 난 굉장히 궁금하지. K를 어떻게 바꿈에 따라서 루트가 어떻게 바뀔 것이고 위치가 어떻게 바뀌냐에 따라서 리스폰스가 어떻게 바뀔지 완전히 바뀔 거 아니야. 알고 싶은 거야. 어디다가 K를 놓으면 좋고 K를 어떻게 바꾸면 리스폰스가 어떻게 바뀌냐, 어떻게 K를 설계를 해야겠다. 그런 게 중요하겠지. So, I want to find out how the system response will change depending on the values of gain K, right? So how can I find out that? How can I do that? The best way is plug 0, 0, 0 and calculate the poles. Plug 1, calculate. Plug 2, 3, 4, 5, 6. Repeat, 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 repeat. Every day, every month, year. You can do that. So you can, these are the poles for K1, for K2, something like that. This is meaningless, right? It's a waste of time. It's very silly. 이렇게 굉장히 어리석은 짓이지. So, in this chapter, look at this. Hey, big question. What decides the system response? What decides the system response characteristics? Location of the what? Location of what pole? Which pole? Open loop pole or closed loop pole? Closed loop pole, location of the closed loop pole decides the system dynamic response. But look at this. Open loop pole, it is very easy to find out. Closed loop pole is difficult to find out. So it might be very nice if we can estimate, 예측할 수 있으면 좋을 것 같아, estimate. If we can estimate the location of the closed loop pole using the open loop pole. 오픈 루프 폴을 이용해서 closed loop 폴의 위치를 예측할 수 있는 얼마나 좋냐라는 거지. That's what we're gonna do. We're gonna estimate closed loop pole location using open loop pole. This technique is called what? Root locus technique. 근궤적이라는. 기가 막히지 않냐? 오픈 루프만 주고 클로즈업을 찾을 수 있게 해주겠다는 거야. So, what is locus? So, this is the subject tracking camera system. 물체를 추적하는 카메라야. So, this system can be modeled this way. Okay? This is my controller. This is my system camera. I can change this K1. Okay? So depending on the value of K1, hey, the closed loop transfer function for this will be this. Yes? And the location, this is second order system, so there must be two closed loop poles. 맞지? So look at this. Depending on the values of K, 0, 10, 5, my closed loop poles, this. Okay? And I'm gonna plot them on this complex domain. 복소 평면에다가 저걸 내가 표시를 했어. So, look at this. Here, 0. 여기 뭐가 있어요? Hey, this black X. Well, this X represents the pole. Okay? And circle represents the 0. Okay? And as you see, this and that is the closed loop pole when K was 0. Okay? And look at this, here. What is the order of this system? Second order. So there'll always be two poles as a pair. 짝으로 항상 두 개가 있어야 돼. So here I have 1, another, at when k was 0. And if I increase my gain k up to 5, then there's another one, another one. How do we know? This. 이거. We just put numbers here. 0, 5, 10. So, when k was 10, there's 2 poles. So, 저걸 여기다 그린 거라고, 2개씩. Now, if I increase the gain k, how my closed loop pole is moving? Look at that. How my closed loop pole is changing. Okay? It was here, 5, 10. If I increase my gain k, this pole was moving this way. And this pole was moving that way. Correct? And if I increase even more, 10, 15, 20, 25, 30, 35, it's going that way. This one is 5, 10, 15, 20, 13, going that way. So, first pole is moving this direction, second pole is moving that direction, and finally it's going that way, and this pole is going that way. So what this graph means? 이 그래프가 뭘 의미해? 이게 바로 뭐야? 궤적이지. This is the trace. This is the locus of what? Closed loop pole의 locus야. So this is the locus of the closed loop pole. So if I draw it a little bit more simply, this is going to be something like that. This is the root locus. Okay? So why is this important? So if I increase my gain k up to 25, what will be the system characteristics? If gain k was less than 25, where my poles are? Where's my pole when gain k was less than 25? 0, 10, 25. So every pole when k was less than 25 is here. That means my poles somewhere like that. So, in this case, we have 3 different characteristics for the second order system. Overdamped, underdamped, critically damped. What is it? Why is it? Why is it overdamped? This angle is related with the function of damping ratio, right? This is 90 degree, right? So what is it? $90 degree means damping ratio is 1, right? So, and if my gain k is larger than 25, then what happens? The pole is moving this way, that way. So the poles are somewhere here. That means this angle is less than 90 degree, which means damping ratio is smaller than 1. So this is underdamped. No, underdamped, right? So depending on the range of the gain k, system response is completely different. So using this graph, we can find out the system characteristics. That's why this is important, okay? So in this chapter, we need to draw, so by the end of this chapter, you must be able to draw the root locus for any system. Okay? 어떤 시스템에 대해서도 root locus 그릴 수 있어야 되지. Okay, so before we further, we need some mathematical background, which you don't like. Okay. Okay, 여기서 우리가 복소수, complex number에 대해서 얘기할게요. So any complex number can be represented by what? real part, imaginary part. Okay? And graphically, what? Real part, imaginary part. And this complex number can be what? Real part, omega. So, complex number can be represented as a vector, right? That means the magnitude of this complex number is what? This. This is the magnitude of this complex number, S. Okay, so the magnitude of this is M, right? And how can we calculate that? That is, right? And what is this called, this angle? This is called the phase angle, right? Phase. This phase angle is calculated by what? What? Arctangent. Arctangent, real part, imaginary part. So, real, imaginary. So, arctangent. Okay? Right. And another one is, so what is this? It's a function. It's a complex function. Right? Or what is this? This is complex function, right? 복수함수. And well, 여러분 이거 유리화 가능하지 나중에. Even though actually this is the complex function, if you do some, calculation, it's going to be something like that, right? Real part and imaginary part. So even this complex number can be represented by real part of G and the imaginary part of G. We already know that, right? And look at this. S plus A means if you plug sigma plus j omega into here, it's going to be this. 맞죠? Right? So these are my real part, this is imaginary. So my real part is now sigma plus A. Imaginary is this. We can write this way. And another problem. This function can be represented this way, but at the same time, it can be represented in this way. How? 시그마 플러스 j 오메가 여기 원래 이게 있었잖아. 근데 여기가 뭐야? 뭘 가지고 있어? Here I have 0 at minus a. Right? I have 0 at minus a. So I put my 0 circle at minus a and just connect from here up to this. This vector also represent this complex function. 이 벡터가 이 complex function 나타낸다. Okay? So you can represent this vector in this way or that way. It's the same. All right, look at this example. S plus 7. And if my S is 5.2j, then what? Minus 7. 5.2j, connect. So this is the vector for this case. Okay? All right. So let's say this is my complex function. Complicated complex function. 복잡한 함수야. So you know this symbol. What is it? It's a factorial. 곱하기. 여러 개가 있으면 여러 개 곱하기. 이런 거지. Like this. These two is multiplied. So this can be represented by this pi. And in this case, n would be 몇 개를 지금 곱한 거야? 이 경우에 2. It should be 2. So P1 will be 3, P2 will be 5 in this case, right? So let me ask you a question. this complex function is a vector, so that means it must have its magnitude and its phase. And how can I find the magnitude of this function and the phase? The magnitude is like that. So 이걸로 합시다. You better, well, 이거부터 합시다. So if this is my f, how can I calculate the magnitude of f? Is, what does it say? Zero length를 multiply 하는 거죠. That means the length of this vector multiply. 곱하라고. 그 크기를 곱해. 그 다음 뭐 여기는 pole length. This is the pole, right? Since this is the vector, it has a magnitude, calculate it and multiply it. And divide it. 자, 이해가 잘 안 되지? 뭘 안 돼? 중학교 수학 수준이구나. Okay, let's take a look at this example. It makes you clear, okay? So, this is my function, and this is my s. Then how can I do that? What? I have 1, 0 at minus 1. I have 2 poles, 0, minus 2 poles. And this is what? This is my s, 3.4z. So, right? From 0 to my target position, connect. From my pole, from my 0, target point, connect. Okay? 세 개의 lines, we have 3 lines, 3 vectors. So, this is my f, and the magnitude of this f is what? Magnitude of this, magnitude of that, magnitude of that. 이거의 크기를 요거 크기로 나누면 되는 거죠. So, what is the magnitude of this? That is, this is s plus 1, right? The length of this vector is the magnitude of this. 그렇죠? How can we calculate the magnitude of this? How? This is 3, so this is 2, this is 4, so 2 square, 4 square, that is magnitude, right? Or, 여러분 머리 쓰기 싫으면 기계적으로 하면 돼. 어떻게? You can plug this into here. Then it's going to be, if you plug this here, then it's going to be here, this. And if you plug this here, you will have this. Right? You can calculate the magnitude of this. How? 2 square, 4 square, square root 20. 3 square, 4 square, add. Clear? Not clear? 아, 뭐야. 이거 크기는 뭐야. 그잖아. You just multiply, so that makes this, right? And eventually divide this with that. You make that. So this is the magnitude of this function for this point. Or 이거는 수학적으로 이렇게 계산하는 거지만, or using this graph, you can calculate the length. You can calculate the length, and what? 그 다음에 어떻게 해야 돼? 요 length를 요 두 개의 곱으로 나눠주면 되는 거지. 왜? This is the length of 0. This is the length of a pole. So, what did you see? divide the length of 0 by length of pole. 제로 랭스를 폴 랭스로 나눠버리면 된다는 거예요. 제로 벡터의 제로 벡터의 크기를 폴 벡터의 크기로 나눠버리면 매그니튜드가 되는 거죠. 오케이? 아주 심플한 산수잖아요, 이거, 그지? Okay? So you can divide this vector by the multiplication of these two vectors. Then you will have this. What about the angle, phase angle? Again, if you don't want to use your brain, you can follow this. How? So this is my function. So how can I compute? The phase angle of this is what? Arctangent, what? Real part, imaginary part. What about this? Arctangent, real part, imaginary part. Arctangent, right? And how can we do this? Calculate that. For the phase angle, we do not use multiplication and division. We use what? Add and subtraction. 그래서 이거를 해서 actually the multiplication of this, when you do the phase angle computation, it should be added. And this division must be transformed into subtraction. That means this minus this minus that. 이렇게 하면 되겠죠? Right? So this equation says that. Or another way is, normally you may not going to use this one. Normally, the simplest way is looking at this diagram. So this is the zero angle, this is pole angle. So zero angle에서 from zero angle, you need to subtract these pole angles. Because of this. zero angle에서 pole angle을 빼. Why? Because zero angle은 분자하고 pole angle은 분모에 있으니까 여기서 이걸 빼줘야지. We need to subtract the angle from pole from the zeros. So how can we calculate the angle? How? Angle always measured from the positive real axis. 앵글은 항상 양의 실수축에서 계산돼야 돼. So the angle is what? This. This is the angle for this. How can we calculate? This is 90 degree, and this angle is what? Arctangent 4분의 3. Okay? So this angle is 90 plus arctangent. So this is the angle for this pole. What about this? 말해봐. Speak. What's the angle for this? Angle of this 90 degree plus what about this? 90 plus 1, 4. So it's going to be, right? So in the end, what? 이거는 뭐야? These are 0 and 4, 4. So 0 angle은 plus, 4 angle은 minus. Add all together. Okay? It's quite simple. Clear? Clear, unclear? Clear? Must be right? 이런 툴, 이거 너무 간단하잖아. 이런 걸로 하면 서로 좀. 쪽팔리지? 바로 넘어갈게. Alright, so, now. 여러분, 여기서부터 잘 들어야 돼. 뭐냐면, 나머지 우리가 한 달 반 동안 공부하는 게 컨트롤러 설계잖아. 이 루트 로커스 테크닉을 이해하지 못하고서는 컨트롤러 설계는 깨끗하게 잊어줘야 돼. 오케이? 깨끗하게 잊어도 돼. 근데 아무튼 나머지 부분을 공부하고 싶다니 루트 로커스 완벽하게 이해해. 특히 이 페이지, 이 개념에 대해서. 자, so what was locus? What was it? 얘기해봐, speak. 자취. 자취. 뭐해? 아직은 좀 정리가 안 되고 있죠. 루트 로커스가 뭐라 그랬지? K를 키움에 따라서 클로즈 루프 폴의 위치가 변하는 걸 그림으로 보여주는 게 루트 로커스라 그랬어. 그런데 그거를 내가 매번 클로즈 루프를 계산해서 찍어 놓는 건 멍청한 짓이지. 루트 로커스의 가장 큰 장점이 뭐야? We can draw the root locus using open loop pole. That is the major advantage. Okay? Alright, look at this. So this is my closed loop system. This is my transfer function. Okay? So what is my characteristic equation? This is my characteristic equation. 그죠? So big question to you. Big question. What is the closed loop pole? Tell me the answer using this characteristic equation. 기말고사 2점. Extra 2 points for the final exam. What is the closed loop pole in terms of this characteristic equation? 점. 안타깝네. 5점. 안 가죠? 내가 가질게. 회수. What is the characteristic equation in this case? This is the characteristic equation. Do you agree? What is the closed loop pole in this case? What is the closed loop pole? Any value that satisfies this equation, that is the closed loop pole. 이걸 만족하는 어떤 S 값도 closed loop pole이잖아, right? So S2 these are the closed loop poles that actually satisfies this equation. 만족시키잖아, right? So this is my characteristic equation. So any closed loop pole which is S must satisfy this equation. That means KGH must be -1, right? But in the complex domain, the -1 is here, right? This is magnitude of this is what? The magnitude of this -1 is 1. And the phase angle of this -1 is what? Is 180 degree. Two pi plus 100 degree, 3 pi, 4 pi, 6 pi. So we can write that way. 2k plus 1, 180. Right? This is simply -1. 맞죠? k는 뭐야? 이 2k가 있으니 k가 1, 2, 3, if you increase k, 1, 2, 3, 4, 5, it's going to make 1 turn, 2 turn, 3 turn. But after 1 turn, 180. here. 2 turn here. So KGH must be this, right? 무슨 얘기를 하고 싶냐면 이렇게 돼. Listen to me. Any value, well, this was what? This was started from this equation. This one is the characteristic equation, right? So, any value that satisfies this relation is the closure form. 무슨 얘기냐? 이 조건을 만족하는 어떤 값들도 다 closed 폴이 된다는 거예요. 다른 말로 하면 closed 폴이 되기 위해서는 반드시 이 조건이 만족이 되어야만 closed 폴이라는 거죠. Agree? Also, at the same time, hey, listen very carefully. I'm going to call this equation as angle condition. 이거는 분명히 이렇게 시험 볼 때 angle condition을 써라 이렇게 물어볼 수도 있을 거야. 잘 기억하라고. angle condition이 바로 요거라고. 이 각도 조건. So this angle condition must be satisfied to be the closure form. Okay? 싫어? 응? Alright. But look at this. This KGH. Hey. Minus 1. So it was, the magnitude of this was 1, and this was the phase angle. And this was the phase angle of this KGH, right? Phase angle. And the magnitude of this KGH is 1, right? So, if we rewrite, 이거를 다시 쓰면, we can write this equation in this way as well. 이렇게 쓸 수도 있죠, right? And this means what? Hey, any S value that satisfies this equation was the closure form, right? But depending on this K, the closure form will be different, right? But if I say these are my closure form, 이게 만약에 closure form이라면 what was the K value for this case? Depending on the K, closure form could be here, could be here, could be here, could be here, right? K 값에 따라서 여기가 있을 수도 여기 있을 수도 다 다르잖아. 그런데 만약에 if I'm saying these are my closure pole, then I'm wondering what is the K, what is the value of K when these two poles are closure pole? 이게 closure pole이라면 어떤 K 값에 의해서 만들어졌을 거 아니야. 그때 그 K 값이 뭐냐고. That K value can be found by using this magnitude condition. 자, 정리할게. Let me summarize. If you want to find some point, if you want to know some values are closure pole or not, you must check this angle condition. angle condition을 이용하면 closure pole인지 아닌지 여부를 알 수 있어. 만약에 once it is verified to be a closure pole, closure pole이라는 거 확인되면 you need to know what K value was used for those two poles to be the closure pole. That K can be found in this equation. So, this equation is called angle condition. This equation is called magnitude condition. So, angle condition은 언제서 closure pole인지 아닌지를 확인하는 데 쓸 거고, magnitude condition은 closure pole이 확인이 됐으면 그때 K 값이 얼마인지 알고 싶으면 magnitude condition 써야 됩니다. 이 페이지를 이해를 못하면 앞으로는 내가 볼 때 굉장히 곤란해. 이해했어? Everything clear? No clear? Hey, look at this. 만약에 So, if this is my characteristic equation, okay? My characteristic equation is this. Oh, wait a second. this is my characteristic equation. 1 plus k gh. This is my characteristic equation, right? And I want to find out, let's say, minus 1.2j. Let me ask you a question. Is this the closed loop pole for this system? Do you know? 이 점이, this point, is the closed loop pole for this system? Is it correct or not? Answer in 1 second. I don't know. But there is a way to check. How? A, G, H must be so 이 점은 I'm going to plug this point into here and calculate the angle, and if that angle is that is the closed pole. If that angle is not this, that is not closed pole. So let's look at this. So 형훈아, 따라오고 있어? Okay? So this is my open loop transfer function. This is my closed loop transfer. 이거 맞을 수 있지? You can make this, right? So 여러분, look at this. My open loop system has 2 poles, 1, 2, 2 zeros. Okay? Right? Correct? And I want to know this point is the closed loop pole of this system or not. How can we check? So look at this. I'm going to make up 다리를 내릴까요? 다리를 만들어. I'm going to make a connection. Okay? And calculate the phase angle. How? If I call theta 1, theta 2, 3, 4, then what should be the phase angle for this case? 0, 0, 4, 4. So, phase angle 0, summation of phase angle 4. So, add, subtract. 더하기, 빼기. So, look at like this way. Huh? 0 angle, phase angle, 4 angle. 1, 2, 3, 4. 이거, can you read in Korean? (56) Okay? 71, 90, 108. This is 70 something. So, is this the closed pole or not? If this is the closed pole, this phase angle must be minus 100 or 한 바퀴 돌아서 100. So, it must be but this is not. So, this is not the closed loop. Okay? Okay? So what about this? Another point. 2.3j. Oh, it's not. So this one. Let's check another point. So this is maybe somewhere here. Another point. I want to know if this is closed loop or not. How can we find out? Now, look at, hey, 여기 봐. 여기가 이 점이 클로즈 폴인지 알고 싶어. 어떻게? check angle. Let's assume that was 180 degrees. That means this point is the closure pole of the system. Okay? But it's not done yet. 아직 끝나지 않았어. What? I want to find out what was the gain K when this value was the closure pole. Because when my K was 0, the closed loop pole was here, increase the gain K here, 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 finally it is here, right? So, what is my gain K when this pole is closed loop pole? How can I find? Angle condition, magnitude condition, what? Which one? Magnitude condition. So that is, what was the magnitude condition? This. How? 이거 잘 봐, 여러분. 이건 뭐야? GH의 reverse, 역수야, 역수. open loop transfer function은 뒤집어 버리는데. It's a reverse of the open loop transfer function. 자, now, so this is my open loop transfer function. 여러분 잘 봐봐. 이게 KGH잖아. 이거 1이 돼야 되냐면 K를 어떻게 찾아? K는 여기가 GH, 이게 GH니까 이게 1이니까 K는 GH분의 이렇게 돼야 되잖아. 뒤집으면 원래는 여러분 어떻게 돼야 돼? 제로 랭스에서 홀 랭스를 이렇게 해야 되는데 뒤집어졌으니까 홀 랭스를 제로 랭스로 나눠야겠지. 그러면 이게 뒤집혔으니까 reversed, we have this. 그런데 지금 what is my test point? This. So you can plug here, 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 here. We have this. You can compute, right? You can calculate. 할 수 있지, magnitude? Which means what? When I increased my gain K up to 0.33, this point will be my closed loop. Okay? 이거 여러분 이렇게 계산해야 돼? There's another way. We can calculate the length of this L1, 2, 3, 4. So multiply. So in that case, what will be the magnitude? L1, 2, 3, 4? The K will be L3, L4, L1, L2. Because 제로 랭스, 폴 랭스인데 뒤집히니까 폴, 0, 0, reversed. So, this way. Clear? This is the fundamentals. 이게 아주 기초적인 거예요. 이걸, without this, you cannot proceed anymore. Okay? Okay? Just, 여러분, what is the pole? What is the pole? Any value that makes my function goes to infinity. Right? 자, 여러분, 이거 뭐야? 여러분, 폴은 우리가 맞지? 그런데 제로는 뭐지? What is zero? 시스템을 0으로 만드는 게 제로지. If my s goes to infinity, what happens? That means we have zero at infinity. 무한대에 제로가 있는 거잖아. 0으로 가버리니까. 그렇지? So, in that case, we can say this is infinite zero. Okay? What about this? Hey. 이게 뭐야? If my s goes to infinity, then what happens? This g goes to infinity. That means I have a pole at infinity. So this is called infinity pole. Okay? 여러분 이거 알아야 돼. Keep in mind, any system, 여기 봐. Look. 여러분, finite pole, finite zero라는 것은 뭐야? 크기가 유한한 폴이야, 제로고. infinite pole zero는 무한한 크기의 폴 제로야. 폴, 무한 폴, 유한 폴을 다 더한 것의 개수하고 유한 제로, 무한 제로를 더한 개수는 항상 반드시 똑같아요. They must be the same, the number. Okay? So look at this. So, where's my pole? 0, minus 1, minus 2. I have 3 finite poles. Do we have finite zeros? No. So no finite zeros. But if s goes to infinity, s가 무한대로 가면 어떻게 돼? 1, 2, 무한대로 더해봐요. There's no meaning adding 1 and 2 to infinity. So we can approximate, we can approximate, 이렇게 근사할 수 있죠? When s goes to infinity. So in this case, if s goes to infinity, this value will go to 0. That means at infinity we have 0. But how many? 1, 2, 3. So I have 3, 0, right? So we have 3 infinite zeros. No finite zeros. 3 finite 4, 0, 5, infinite 4. So numbers, if they sum, always same. Lucky. Lucky is very lucky. Why? The poles, you boys. Zeros, you girls. The number is always the same. They are always your partners. somewhere. 여러분 짝이 어딘가에 다 있어. 걱정하지 마. But you're just laughing at me, right? But in the next class, this fact, same number, will be a key player. 다음 시간에 굉장히 중요하게 쓸 거예요. 짝이 같다는 거. Okay?